Okay, so if you look, what's the last thing on your handout there? Kepler's Laws. I don't care too much about Kepler's Laws, with the exception of the third. You should kind of have a general idea of what they mean, but the third one is the only one that really has any mathematical application for you. So, but Kepler's Laws deal with the planets. The planets actually go around the sun in what kind of orbits? Yeah, it turns out they're elliptical orbits around the sun. So they're not circular, they're elliptical. And so that's kind of what Kepler's Laws deal with. And he talks about the planets have elliptical orbits with the sun as one of the focal points. So it turns out when you're in an ellipse, so across this major, we'll call it semi-major axis here, so you have two focal points. The sun is one of them, is all they're saying. So it means more than that, but I don't care. It doesn't mean anything more than that to you. You should just know the definition of, you should know what Kepler's first law says. It also says that the line between the sun and a planet sweeps out equal areas in equal time intervals. You know what, let's make this a little more lopsided here. Let's say this looks more like the orbit of a comet instead of a planet. Works for anything orbiting around, any kind of planetary motion we're talking about. So in this case, comets orbits elliptical. Sometimes it's closer to the sun, sometimes it's further from the sun. When does it have more potential energy? So when does my marker have more potential energy? When it's closer to the Earth or farther? So we have more potential energy out here. And if we have more potential energy out here, then we have less potential here. So if we have less potential, we have more kinetic here. And so if I look at a given amount of time, so I might have a planet in a given amount of time going from here to here, and I might look at this area distended right here. If I looked at that same time interval on the other side of its orbit, I might find that it travels a lot smaller distance. Why is that again?
Because it has more potential.
Has more potential and less kinetic, so it's traveling slower overall. But if I look at the overall area, as long as, again, these are equal time intervals, then the area of this triangle and this one would theoretically be the same, even if it doesn't look that way on my drawing. Cool. So that's Kepler's second law. He says just in equal time intervals, so a line from the center of motion to the orbit distends the same area in the same interval of time. Cool. Now the last one, Kepler's third law, is the only one I really care about. So it says that t squared, the period of orbit, is proportional to the average radius cubed. That's what it says. And actually, he shows there's a proportionality constant. He called it the Kepler constant and stuff like that. We're going to derive what that Kepler constant really is. Now, instead of dealing with an elliptical orbit, we're going to have the easiest elliptical orbit you could ever deal with mathematically, which is circular orbit. So in this case, we got the sun, and we're going to have the Earth or some such planet going around in a perfectly circular orbit in this case. What forces are acting on the planet? Gravity. Pulling it towards the sun. Cool. Anything else? No. And some of my forces would add up to, in this circular motion, so GM1, M2 over R squared, and it would add up to mv squared over R. So same kind of thing we just did a second ago back here. So in this case, we'd have G, we'll have mass of the planet, mass of the sun, all over, and here I'm going to call it the average radius of the orbit equals mv squared over R. Again, this is the mass of the planet. Cool. So again, we just derived some of the forces equals mv squared over R for the radial direction. So we want to somehow come out with a period, though. So a couple questions here. In one complete revolution, what distance has that planet traveled? It's traveled the entire circumference of a circle, which is 2 pi r. Cool. And what I'm wanting, the period here, capital T, is the time it takes for that to be accomplished. Okay. So if you guys recall this lovely equation, so when you have constant velocity, no acceleration, this is all you got, right? Well, in this case, we can't really talk about displacement. We're not going in a straight line, and one complete revolution with zero displacement. So we're going to look at kind of the distance equivalent here in this case. So, and looking at just speed rather than velocity. So, but here, the entire arc you distend, one full circle, 2 pi r, is v times t. And so in this case, if I solve for t, I get delta s over v. And in this case, I make it a capital T for a period. That means the distance I've traveled is 2 pi r divided by the velocity. Cool. So what I'm going to do is take and solve for velocity right here and plug it in right here so I can relate something with my period. So if you recall here, we've kind of already derived this. So our v is going to be very similar here. What are we going to have for that velocity? Oh, let's get rid of the mass of the planet too. And we'll just call it the average radius of the orbit here. So actually we'll make that the lowercase r as I did there. Cool. Anything else? That's actually it. No, in this case, it's not like going around the Earth. Yeah, so it's the radius is to the center of the sun. So that's it. And we're going to substitute that in right here. So we'll get t equals 2 pi r over the square root of g, mass of the sun, over r average. And what do I need to do here? So this doesn't look pretty. How do I derive something looking like this? Yeah, let's square both sides, get rid of this whole square root term. Actually, 2 pi r is 4 pi squared r squared all over g, mass of the sun, over r. And if you notice, dividing by something over r is the same thing as multiplying by r. So I'll get rid of it and make this r cubed. And all of a sudden we have Kepler's third law. T squared is proportional to r cubed. And our proportionality constant is 4 pi squared over the gravitational constant times the mass of the sun. So here's the deal. So this is Kepler's third law. This is formally the exact mathematical representation of Kepler's third law. You may be asked to solve for something like the period going this route. So do you want to memorize Kepler's third law? Maybe. So I personally like deriving an equation for the velocity from my sum of the forces equation, and then using 2 pi r over velocity if I need the period. So I don't have this equation memorized. So however you want to do it, if you want to memorize this equation, more power to you. So your choice.